Hi to everyone. Welcome to this joint webinar of M+P and Kistler on practical consideration of force-limited vibration testing. Please be aware that you're muted per purpose and that this webinar is recorded. The recording will be shared and sent after the webinar. If you have any questions, feel free to use the Q&A section on the right-hand side. We will answer your questions during the webinar or at the very end. My name is Pascal Erni and I'm Business Development Manager at Kistler for Test and Measurement. Today we have two highly experienced personalities who will share their know-how with you. On one hand, there is Chris Wilcox from M+P, Sales Manager and being in the business for more than 22 years, with experience in vibration testing of large spacecrafts, vibration control, model and channel data acquisition, thermal vacuum operation, and acoustic testing in different positions as test technician, consultant, account, and sales manager. On the other hand, we have Bill Zwolinski, working for Kistler for more than 20 years. Bill holds a master's degree in electrical engineering, specializing in signal processing and controls. Before joining Kistler, he was working in the field of underwater acoustic and was chief engineer for the Navy carrier landing systems at Textron. With this knowledge with his knowledge in electronics and mechanical engineering, he completes this enormous load of knowledge for this webinar. And now I would like to hand over to Bill. Bill, the stage is yours.
Thank you, Pascal. Okay, so the agenda for our webinar today is as follows. I'm going to cover more force instrumentation topics, a little background on force-limited vibration, and then Chris Wilcox is going to handle the vibration control topics and the details you see listed below. Just for some background on force-limited vibration testing, I mean, it's always good to think about, how does a payload actually, get launched and get deployed out into space. And I saw this illustration in a paper I was reading once. I said, this is really, I think, makes a nice summary, of some of the challenges that a spacecraft, a payload sees. So you can see at the early stages that there's quite a bit of high-level vibration, followed by maybe lower level vibration and transient impulses due to separation events and so forth, and eventually the payload is deployed. So I mean, you can see that it's ultra critical that the payload itself is not only is surviving this period of launch and deployment, so that it could follow on with its critical mission. Environmental testing, you heard Chris Wilcox is pretty expert and occupied a lot of these areas, that I list here, but vibration testing, shock testing, vibroacoustics, electromagnetic and thermal vacuum testing. So, force limited vibration is another component of environmental test, and it's really looking at, looks at performing extensive ground-based testing to ensure that payloads are mission ready and operational after launch and deployment. Force limited vibration, if you take a look at a simple rendering here, you see basically a slip table, and on the slip table you'll see force sensors with a ring, and you'll see a test article. Okay, so conceptually this is what's going on is you're using these force sensors to monitor the fixed base resonances between the shaker and the test article, and facilitating a control solution that mitigates any resonances or notches resonances at the fixed base interface. You can see here that also there's many components that comprise a force limited vibration test, and I just illustrated a few there, but certainly the shaker controller and force sensors and signal conditioning are some of the key areas, as well as the shaker itself. There was some instrumentation done some time ago on the GLASS mission, where they actually instrumented for acceleration and forces during liftoff and flight. And I thought that would be interesting just to say take a a peek at this and see exactly what's going on. You can see that, in the top picture here, you can see it's acceleration versus frequency, and there are certainly considerable levels of acceleration, certainly at liftoff and certainly during flight. Certainly in terms of the force profile, you can see that upwards of, say, almost 5,100 pounds of force, 2,300 kilonewtons, could be also present during certain aspects or certain frequencies associated with launch and flight. So you can see that they're considerable. So, that's a bit of motivation associated with looking at a force limited vibration test. So, force limiting basically replicates this test article resonant response for the actual flight mounting condition. The flight equipment itself is typically mounted on a relatively lightweight structure, which has a mechanical impedance comparable to the mounted equipment, where shakers, on the other hand, have a near infinite mechanical impedance. And as you see here on the right-hand side, you can see a simple schematic of a shaker system, force sensors at the interface between the test article and the shaker, accelerometers, of course, signal conditioning, and the vibration controller itself closing the loop. Obviously, traditional vibration testing really controls on the input acceleration to the frequency envelope of the flight data. Limiting on the test acceleration responses to those predicted in flight often requires quite a bit of analysis, usually requires limiting the acceleration response at many locations. That, coupled with the high shaker forces at the resonant frequencies of the test article because of the mechanical impedance mismatch, results in really an over-testing and could be possible damage to the unit under test. So alternately, the limiting of the input force at the fixed base resonances of the unit under test is less dependent on analytical models and provides automatic notching without over-testing. So really the purpose of force limiting really is to automatically notch the acceleration at the test item resonances by measuring and limiting the reaction forces between the test item and the shaker table. So, in the control solution, it's you're really looking at many inputs, and an extremal control solution will basically limit on the basis of the maximum, say, several inputs entering the control system. So conceptually, at frequencies other than the test item resonances, the acceleration test specification usually controls the test. However, at the test item resonances, the base reaction force increases, and then the force control specification is limited, per some predetermined limits. The force control limits are certainly based on legacy flight data, as well as analysis and added safety margins to ensure a proper test. And then just out of the handbook here, out of the NASA handbook or report 1403, you can see just a simple illustration of the envelope of the vibration data, and also what could happen if you have an unlimited input force. You get perhaps an exceeding of 10 dB at a certain frequency, whereas force limiting would actually counter that effect and actually act to normalize or limit that event from even happening and possibly damaging the structure itself. So the next step is really to try to get into a little bit about force sensors and multi-component force measurement, because this is definitely at the heart of force limited vibration. So what you see here is basically a 3-component force sensor, and it's often integrated into dynamometers. It could be square, rectangular, triangular, circular dynamometers, which measure multi-components, typically 6 components of forces and moments of the reaction forces. Some terminology, piezoelectric and IEPE sensors. Basically, piezoelectric sensors do not have any electronics inside, and they rely upon an external charge amplifier. What this does is the external charge amplifier is very capable to range the measuring chain for whatever measuring ranges are of interest. And so this allows you to optimize the dynamic range of the measuring chain to the actual application because of the flexibility of rangeability. Also, when it comes to instrumenting your platform and with force sensors, there's a preload operation which requires a quasi-static operation. Well, piezoelectric sensors with a quasi-static charge amp allow measuring of these static or low frequency forces to make sure that it's properly preloaded. We're going to talk a fair amount of preload as we go forward. With IEPE, on the other hand, you have a sensor that has integral electronics. Obviously, a lot of data acquisition systems nowadays support an IEP supply right on the channel, the data acquisition channel. With this type of a sensor, it's usually considered primarily dynamic only. So it's a challenge to preload an IEPE sensor for sure, because of the low frequencies are not down to zero. They're usually more AC coupled systems. So and then obviously the range is fixed, and there's really no, as I mentioned, no possibility to really measure quasi-statically in that regard compared to the PE. In terms of the frequency response of a piezoelectric sensor, whether it's IEPE or PE, it's basically a single order high pass characteristic on the low end and a lightly damped second order characteristic on the high end. So if you make these assumptions and look at the frequency response, you can often tailor some closed form expressions, or at least approximations to amplitude response as a function of natural frequency. So if you knew the natural frequency of your vibration fixture with a mass on it, you can estimate the 5% frequency as FN over 5. The 10% is FN over 3, and the 3 dB is FN over 2. So the 5% frequency would be roughly where the amplitude response will vary plus or minus 5% over that frequency band. So if you put a unity sine wave in over a 5% band, you would expect a 0.95 or say a 1.05 out, a 5% tolerance, if you will. So just to give an example. Oftentimes you want to keep that in mind as you build up fixtures and quantify what your natural frequencies are. You can use these rules of thumb as a guide as to what amplitude response tolerance you need to accommodate a certain frequency requirement. On the low end, I talked about the high end just recently. On the low end, the single order high pass characteristic is a pretty well known filter methodology. But there's a parameter called time constant, which basically dictates where the cutoff frequency of the high pass characteristic is. I give some closed form expressions here as to where that time constant is and what the actual 5 and 10 and 3 dB frequencies would be. The important takeaway here is really when you put forth your measuring chain, you want to ensure that the low frequency characteristic as well as the high frequency characteristic is accommodated by your signal conditioning. So it's important to take a look at that, because a lot of times in charge amplifiers, the actual time constant or the low frequency characteristic could be a function of the actual measuring range selected. So it's always important to pay proper attention to that to ensure that your measuring chain has full coverage over the frequency band of interest. Dynamic and quasi-static charge amps, I think it's pretty straightforward. Dynamic certainly are going to measure all the vibratory characteristics of a force limited vibration test. But certainly with the preloading side of it, where you get a static force or quasi-static force, it's really not suitable for that. Whereas a quasi-static amp does both the dynamic and the low frequency or static measurement. And you can see here in the illustration, we not only measure the dynamic vibratory testing, but also the quasi-static testing or setup during preload. So that's very much important to ensure that you have the right installation. So we're going to talk a little bit more on that in a few minutes. Just to give an example of some charge amps, and there's all kinds of charge amps out there. Certainly, I think dynamic charge amps only we won't consider them exactly at this point, but there's a quasi-static and dynamic charge amps together. As I mentioned, they give basically a complete solution for both preload and also the force limited vibration testing. Some of the key takeaways, in terms of looking at amplifiers is really the measuring range. A lot of times measuring range is important. You may have to exert a very high preload, for example, on a force sensor. So you want to ensure that you have a very high measuring range capability. What a charge amp does is basically takes the piezoelectric signal and converts it to a representative 10 volt, plus or minus 10 volt signal. The bandwidth of a charge amp typically is quite wide, so it's probably rare that you'll ever see that the high frequency characteristic of a force limiting test would not be covered by a charge amp. But you always want to check and pay attention to the low frequency, and because not all charge amps are created equally in that regard. I mentioned rangeability, and just a simple example of rangeability. What you see here in the piezoelectric sensor, it might be a 10,000 Newton sensor, and you have a simple cable and a charge amp. You can range that sensor for anything from, I just show an example down to 1 Newton. And what you see here is the actual noise voltage, RMS noise voltage, actually decreases proportionally as a function of measuring range. So you really, get a very, we call the magic of rangeability. So you actually get a very low noise solution as you go down in measuring range, and it's really the attribute of an external charge amp that's working for you. Obviously, with this type of a system, also you're able to reset and operate, so that gives you the ability to basically tear the system for any static loads that you might have, static weights, and in that way you can optimize the actual measuring range of the measuring chain on the dynamic or quasi-static portion of interest, and certainly allocate the dynamic range to the data acquisition system and control systems doing the heavy lifting associated with force limited vibration. So there's also other charge amps, and they're more multi-channel, digitally processed charge amps. And these here offer some fairly unique capabilities. A lot of time they've got integral data acquisition, as well as obviously perform the rangeability features that I talked to previously, which is a very important feature of using piezoelectrics. Certainly for force limiting, the rangeability is a key benefit, I think, for the measurement. You always want to allocate the dynamic range appropriately to the measurement. Obviously, individual sensor channels, X, Y, and Z's, can be fed directly to a M+P controller. And so what you get there is you get total visibility of every channel of your measuring chain. So no need to pre-sum with these types of amplifiers. And certainly with the integral data acquisition, you not only have in an M+P controller system, you'd have recording of data, but you also have the ability to do a backup recording as well with the lab amp with the integral data acquisition feature as well. In terms of force dynamometers, I mean, a force dynamometer is what I showed earlier. I think it was the first slide. I showed you the circular ring and force sensors. Well, that's a pretty good illustration of a force dynamometer. And basically, force sensors on their own, if you look at this force sensor, basically wants to see axial forces. But in a force limiting test, you don't have axial forces. You have a fairly large and complex test article, and you need a way to distribute those forces and moments to sensors. And the best way to do that is to create a force dynamometer, which basically does that. And based upon the geometry of that dynamometer, now you can use that to not only compute forces or measure forces, but also resolve the moments as well. And analog bandwidth considerations, always an important topic when you're looking at doing a force limiting test. Obviously, the charge amp, as I said, determines the lowest and highest frequencies possible. The test article is going to have a certain range of frequencies of interest, and we need to be able to quantify that. And then most importantly, the vibration fixtures need to be able to deliver the performance to measure those frequencies of the test article. So there's quite a bit of FEA and analysis being done on the vibration fixture. Certainly the number of sensors, the stiffness of the sensors, the orientation of the sensors, the materials used for making the fixture itself are all factors which come into play. I show various considerations here in terms of force dynamometers. I'm going to talk about a few of these in the next few slides here. Until we get to that, I just wanted to show a couple of slides on three-component force sensors. And you can see that there's certainly a range where you get capabilities of very low force handling range to very high force handling range. You can also see that in terms of sensitivities, they're roughly quartz level sensitivities, fairly high. Some have different sensitivities based upon either a different piezoelectric material, or perhaps it's a very high range load cell in its own right. What you see also here is crosstalk and linearity. Linearity is a fundamental error source in any measurement. Okay, so having the best linearity relates to having an accurate measurement, of course. And obviously for FEA type analysis, having a good understanding of the stiffnesses, both translational and rotational and bending stiffnesses, are all quite critical to doing a proper model. So all these sensors here you see are going to need a preload, and that's why you see a center hole here. They accept a preload bolt, and I'll get in a little bit more of how that's done. If that's not your cup of tea and you don't want to do preloads, and you can live with the added height of a force link sensor, these are actually preloaded at the factory. They have a top and bottom flange, and they come with a calibration certificate, of course. And these can be easily integrated as well within, say, two parallel plates. I mean, the parameters are similar. Sensitivities, linearities, crosstalks, and stiffnesses are all provided for force links as well. Just to show a little bit more detail on how a dynamometer is configured in the geometry of sensors, this is a simple illustration of a rectangular dynamometer where you see 4 force sensors separated by a vertical distance A to the center and a horizontal distance B to the center. Okay, so as charge sensors can be added directly, okay, charge can be added directly without any added electronics. You can simply do some pre-summing internal to the dynamometer and output 8 signals instead of 12, which gives you a reduced channel count, which reduces cost and allows you to still do multi-component force measurement solutions. With this type of geometry, you can easily compute the closed form expressions of forces and moments. And you say, well, how do you get to those closed form expressions, Bill? And I say, okay, I give you an illustration here on the next page. Now this looks very busy, but I just wanted to give you a couple examples. I mean, here's the x-axis. And if you wanted to see the moment about x, you group the 2 sensors to the left with the 2 sensors to the right, and you then basically difference the 2 pairs of sensors and multiply times the moment arm B, which gives you the moment around X. In Y, you see the same thing, although I'm grouping sensors along the top and along the bottom, and working through a moment arm A, you can see MY is computed in the same way, and certainly the same methodology is used in computing MZ as well. So by looking at the geometry of sensors, you can compute closed form expressions that represent exactly what your vibration fixture has provided. And in terms of any dynamometer, I mean, this isn't, say, a practical way of doing it in a force limiting test, but force dynamometers are often calibrated with multi-component presses, with electric actuators, with strain gauge force sensors for reference, and PE force reference sensors for calibration. So you have the ability to apply very precise forces at known loads and be able to calibrate the entire system, which is obviously not so practical in a force limiting test. So we're going to talk about what we do in those situations in the next few slides as well. Some of the things I talked about in terms of considerations when you're making a dynamometer, the load-bearing surfaces are rather critical. You want to make sure you have a good parallelism and flatness. Obviously, I show here 0.01 millimeters, but on the order of a thou is usually acceptable for a lot of applications. That's roughly 0.02 millimeters. Ideally, you would like 0.01 millimeters. Certainly, high strength materials and having stiffness in your design also contributes to high frequency response. Preloading, very important to getting the most out of your multi-component force solution. The preload bolt, as you see, here's the force sensor in red. You have the preload bolt going through. It has threads on the bottom and threads on the top. There's a ring nut at the top. There's actually a sliding washer right between the ring nut and the surface of the ring of the top plate, and that's greased so that you can get you don't bind up when you're preloading the assembly. So it works quite well and quite easy to use. What preloading does is it really optimizes linearity and stiffness. It really closes any micro gaps in the sensor, and you get very excellent, really good linearity, which is on the calibration certs for sure. It also provides compressive and tensile force handling capability, and also the shear force handling is a function of the frictional coefficient and the preload force. And obviously having enough shear force handling is essential to eliminate slippage in your force limited vibration test. Very critical step to get the best and the safest performance out of your force sensors. The force sensors also, the 3-component force sensors, have a ceramic top coating, which provides ground isolation, and also the increased frictional coefficient that I mentioned of 0.2. So that absolutely complements high shear force handling solutions. I mentioned linearity. Linearity is basically the plot of input force versus output force. The straighter that line through the origin, the better the linearity. So you always want to be sure that the preload gives you the best linearity out of the sensor for sure. I show here also you can do partial range linearity on any force sensor. So it's also something some people, because you can use piezoelectric sensors for many applications, you can get calibration coefficients for various force ranges and just use the proper coefficient for your given test, depending on what your measuring ranges are. Very flexible, very easy to use. A little bit more to do on the front end, certainly when you get your sensor calibrated. I talked about the preload bolt. The preload bolt is basically mechanically in parallel with the force sensor. The preload bolt is going to act as a force shunt. Typically, using Kistler preload bolts, you're going to have between 6 and 9% shunt force, which means that your sensitivity of the force sensor will be reduced by 6 to 9% because some of the force is taken up by the stiffness of the bolt itself. The bolt stiffness is important in this because, as you can see from the calculations, if you have too stiff of a bolt, the actual bolt will take up the force, and the force sensor sees less resultant force, which is not really the best way to go. So you want the proper preload bolt. Tensile and compressive force, usually you preload at 70% of the full scale range, and that gives you basically the ability of measuring both compressive and tensile forces with a margin. Alignment of sensors is critical. As you see, force sensors like this have a flat. They look circular, but they actually have flats on either side of the force sensor. These flats can be used to align the sensor. So you have, you minimize any misalignment. For every 1 degree of misalignment in the sensor, you get a 2% crosstalk between X and Y. So it's one of these things that's practical and easy to do when you have a straight edge on the force sensor. And obviously crosstalk always comes into play regardless of what sensor you're using. The calibration certificate gives the exact crosstalk of a sensor, and it's the best way to see the performance of your sensor and in terms of your particular application. In terms of preloading, I mentioned here, when you're preloading, you have to ensure that the sensor itself doesn't rotate. So there's a couple different methods here. We talk about the cylindrical pin method, where you actually put 2 cylindrical pins near the connector, and as you preload the top plate to the bottom plate and through the force sensor, you don't see that the sensor will rotate because it's constrained at the connector. Another approach is a very innovative approach by an engineering lab. Is they looked at how do you build a vibration fixture with features that you can preload and hold the sensors in place as you preload. So what they did here was they basically built in additional fixturing on the vibration fixture to mate with the flats of the sensor. So when you preloaded the sensor, there was no way the sensor could rotate. Obviously, after the whole preload, these were all bolted onto the actual vibe fixture. They were removed, and all those extra features for preloading did not stay with the vibration fixture afterwards. So they were just used for preload. So always important to keep in mind preloading when you're designing your fixtures as well. It might help you in the end to, and certainly if you have any questions there, you can always consult us at the factory. In terms of preloading, it's like changing the car of your tire, or changing the tire of your car. Is really the way you do it is you don't want to torque down any one sensor to the maximum limit and then go to the next one. Okay, that wouldn't be the right approach. You want to use say a crossing pattern or star pattern approach, and basically that's what's done. And you basically go to a 25% standard. So if you have a full preload, say of 100% preload requirement, you take 25% increments and repeat it 4 times. In this way, you get even load distribution, you get the good preloading methodology. And what I always recommend is that you make a checklist sheet that's actually signed off or initialed by the person preloading, so you know exactly how much preload was done, each step was performed, because preloading, as I said, relates to shear force handling through the frictional coefficient, and that relates to eliminating the possibility for slippage. So all that stuff is interleaved, so you'll want to be sure you've properly documented that. As a spring mass model, a dynamometer is going to be susceptible to reduced natural frequencies with mass. Keep that in mind. Although with a piezoelectric system, you can tear out the static mass, the sensors are still physically seeing that mass and will be affected. The natural frequency of the spring mass system will be affected. So you always want to factor in the amount of mass in terms of your overall fixture design and meeting the requirements of your force limiting test. This is an example from NASA. It was a global precipitation satellite, basically a large observatory, upwards of 7,000 pounds or over 3,000 kilograms. Frequency range was only 5 hertz to 70 hertz. 3-inch thick top and bottom plates of aluminum were used. Ring diameter was 102 inches or 2.6 meters, 12 sensors. Some of the highest stiffness sensors around were being used to accommodate the large mass of this test article and the frequency response requirements. Preload was done in 25% increments, as I said, in a star pattern, and custom bolts were used in this force limiting test. Obviously, the calibration the in situ calibration will account for those bolts, in terms of shunt force, their shunt force contribution. Just a simple example of what this 12 sensors might look like. You can use geometry again to compute the forces and moments, much like what I did in the rectangular design. A little more complex when you have more sensors in a circular orientation, but certainly straightforward if you use the proper method that I described earlier. You can also see that there are estimates of allowable force and moments based upon maximum shear and axial forces on a number of sensors, and what the sensor capability itself in terms of load handling is. Certainly you can look at maximum bending moments and overturning moments as expressions I have shown here, and it gives you an idea as a rule of thumb as to, is your design meeting the basic requirements. So you can see here, using a 9077C, we can see that we have sizable load handling, maximum load handling, and maximum overturning moment handling capability for this orientation. Obviously, more simulation, or simulation or FEA is always supporting, any final implementations in terms of overall loads and moments to ensure there's adequate margins. So these rules of thumb anyway help you get close and see what works and what needs further work to satisfy requirements. The force ring preload for the NASA test was really following all the rules that I've talked about here. And you can see here at each stage, the force sensors were laid out. the top plate was put on, and then the preload bolts were added, torqued down, and so forth. So all following proper procedure as formally identified. In terms of in situ calibration, I show here out of the handbook 7004C. Basically, you want a low-level sine sweep or dwell below the first resonance, and you want to compare the known mass acting upon the sensors versus the apparent mass that's calculated due to force over acceleration. Okay, so by doing that, you can come up with the calibration correction factor, and the actual mass acting on the force sensors is actually quite important in doing this. Okay, so one call I got recently was from an application where they were just doing the vibration fixture, so there's fairly low mass acting upon the sensor, and the engineer saw about a 16% deviation between the apparent mass and the actual mass. And what we found out was that we didn't accommodate to add the half the sensor mass and the preload bolt mass in the total mass calculation. Once we did that, the apparent mass and actual mass were fairly close, within say 1%, and the calibration definitely was properly done in that regard. So always take care when you're doing these in situ calibrations to account for all your mass sources acting, so you get the best in situ calibration. Lastly, using static masses, for large 2.6 meter or 102 inch platforms, it's really not practical to use a static mass, but certainly conceptually you can use a static mass to calibrate. Simply put a mass on, put the charge amp in operate, take the mass off, and you'll see a change in the force reading. That should be directly proportional to the amount of mass that was removed. So pretty straightforward. Lastly, as a lead into Chris Wilcox's presentation, we've got the 4 force sensors going through the lab amp charge amps. Dynamic lab amps are used for X and Y channels, whereas quasi-static is used for Z. So to accommodate the preload operation, obviously all 12 channels going into an M+P shaker controller. So at that point, I'd like to throw over to Chris Wilcox, who can also give you more details on the vibration control side.
All right. All right. Thanks, Bill, and thank you, everyone, for spending some time with us today. My name is Chris Wilcox. I'm going to be showing you how we've implemented the force-limited vibration control within the control systems from M+P International. A little background: in 1993, Dr. Terry Chardon spoke with some people at M+P regarding some force-limited vibration testing. We utilized our Unix system at the time. Over the years, there's been some changes. One of the major ones was overturning moment safeties, as well as V-band safeties. M+P International has a long history of vibration control of spacecraft. We were founded in 1980. We produced Unix vibration controllers through till 1999. When I started with the company, they introduced a Windows-based controller, and over the years we've added quite a few features, mostly aimed at the spacecraft or spacefaring systems. Today's latest technology, we allow up to 102 kilohertz on 128 samples while we do vibration control. We can go up to 500 channels in vibration control with time domain storage, all in the same thing. We do force limiting in sine and random out to 2000 hertz. The time domain is attached to the sampling frequency of the control system, so that we can sample at, say, 32,000 samples per second when we run a sine test to 100 hertz. There are no limits to the number of control channels and notching limit channels. And the force limiting functions I will show you today actually extend beyond your hardware count. Here's the basic math. You've seen this before. we've basically brought all of these into our vibration control system. So you can do sum force, root sum square, which is a absolute amplitude, and then the overturning moment calculations. These are all done within the software. No need for the external summing junctions. Here's the classical setup that has been used for many years, where, as Bill pointed out, you have quite a few force sensors. Each force sensor has 3 axes. You then wire each individual one into a charge amplifier, or then into a summing junction, and maybe an overturning moment calculation, and you get something out. As you can see, there's some complexity here, and that is what we are trying to reduce. Here's again the same picture, a little more simplified, just coming into summing junctions, and then from here, we make the big jump, we go to here. Major drawback here is you do need extra channels. However, the channel costs are not that bad. We have now integrated the lab amps into our system, into our software, so that the user has one place to store the data, store the sensitivities, the ranges, serial numbers, all that information is now in the documentation at the end of the test for traceability purposes. Another major benefit is the fact that you no longer need to repatch anything once you start your test. From preload to end of test, you should be able to stick to one patch to your vibration control system. An interesting side effect of this is that in the summing systems of the past, a sensor or cable typically would go bad, and the operator would have no idea that it was bad. In this particular case, we ran a test in 2014 where we did the old system and mixed it with the new system, and they didn't match. And the reason they didn't match was one of the force sensors cables was bad. You see in the plots that it caused quite a bit of a change. Obviously, in a real test, this can cause over-testing of the system. So some of the benefits of our system is simplification. Basically, the less wires, less connectors, less BNCs, more safety. Also, all your force measurements are now stored and monitored so that if there's a failure in a cable, overload, tripped over a cable, the system will catch it and shut it down safely. Overturning moment and summing are performed within the software so that you can change axis by just doing the user interface. And of course, all the complex control methods are still there, your average acceleration, off-axis limits, and then root sum squared limits. Everything that we do is available online. I'll be showing that in a little bit. Some calculated force channels, and all this while doing time domain storage of all your data for all your channels, including your force. This can be very handy when you want to perform a CG, dynamic CG test or verification after a test. The reason that M+P chose the lab amps for this application was that the quasi-static mode of the 5467 allows it to be preloaded out to very high force levels. Additionally, it has the long time constant that you need to use when performing a preload. The software is now integrated, the interface is now integrated, and I'll show you that quickly in a little bit. Basically, all of this information is then also stored in your result file for future traceability. Setting up for a force limited vibration test. You've seen this picture a couple times now in different ways. One of the things that Bill did mention is the fixturing. And the problem you get into with these large rings is that the sensors like to be in a single axis, and once in a while, the connectors are not in an accessible location. We have two solutions. One, Kistler makes sensors with inverted axes, and the other way to do it is we can actually adjust for the off axis of the sensor. However, this doesn't account for cross-axis sensitivity. Within the software, we've instituted the summed force. We basically use what we call a vector add. We leave the weighting at 1, and we can enter a full profile or partial profile as needed. I'm going to show you this in a little bit. For the single overturning moment, we actually offer you'll see it in a second, a pure overturning moment, which is axis independent. This is for when you are creating a simple moment around one axis. So in this case, you only enter the distances for the moment arms in that axis. That is fairly how it was done in the past. As you see on the next screen, by using both the X and the Y axis and the correct math, we can now perform a pure overturning moment. This will account for any offset of your CG, so that if the overturning moment is not all in one axis, we still limit on it and protect your item and protect, in this case, your V-band or your shaker bearings. For demonstration today, I'm going to be showing my simulated system, which is basically all my channels patched back to each other. But I've got 4 3-axis force sensors oriented in this orientation, with 2 of them 180 degrees out of phase to give me an overturning moment. Some of the quick math on it to show you what I've done, but it basically boils down to I have one signal going to 14 channels, and I then split them up and then put notching on each one. Let me switch over to this run screen. There it is. Okay, this is the M+P vibration control run screen. I'm just going to start this up. This would be a calibration where you would bring it up and you would be checking that your forces look correct for the weight that you have. Force equals mass times acceleration. As you can see, I show some different forces. I show my out of phase forces here. Show my in-axis force here, which is now set to 100 foot-pounds. So 100 foot-pounds divided by 0.25 Gs. We're talking about a 400-pound item. Depending on my dimensions here, I'm getting 1,000 pounds of overturning, 1,000 inch-pounds of overturning moment. I'll show you how we set that up now. Now, this is a simplified setup, obviously not for a real test. We would typically have multiple, probably 4 controls and many, many notch channels. But the lab amps are listed within the software, and we enter the sensitivity and then a range for the lab amps. For standard ICP or accelerometers using an external source, we set them up as these are. Each one of these can have a tolerance on them, so that if one does fail, we do get a stop, or we can actually individually notch to each one. As you see here, I have a negative sensitivity on 2 of them, and that's going to give me my 180 degrees out of phase for my overturning moment. First off is a standard accelerometer notch. If we look over in the bottom right, you can see I just want to notch it at the end. Here is the sum in-axis force for the x-axis. Again, notice the weighting is all set to 1, and then it can have its own profile. I made a simple profile here. This can have a shape if you want. I then did it for the y and the z. However, we shouldn't hit those. Now, the next step up is overturning moment around an axis. So in this case, I made it simple. I put it 50 inches out on each side, and then I put a notch profile in. It actually won't hit this one. And then the more important, the overturning moment total. Here's where we have to enter both the X and the Y directions so that it can calculate the individual moments and then do a root sum square to give you the absolute overturning moment in case your CG is off center. So go back to the run window, release it. Now, as it sweeps, you're going to see that it's going to be notching the whole time here on the summed force. And then down here, it's going to go back to the reference profile. Then it will bring up back onto it for the summed force. And pretty soon we're going to start hitting the overturning moment. Now we're on an overturning moment limitation. And if I switch this back, it goes back to the reference profile for a little bit. And then it's going to hit that acceleration. If you notice down here on the left-hand corner, the whole time the throughput has been running. I could have started this at any point. I just have it to start on the run, so I don't end up with too big of a file. Test is complete. Bring your amp down. Go and get your data. So in my result data, I have each individual force. I have my overall control, obviously. And then have my summed force, total overturning moment. I also have my drive signal, which traces right along. Another interesting one is the history, where it does show me which accelerometer was or force was in limit by channel number in the upper left. Period. More importantly, I now have my time domain. This takes a second to load, so I can see what I can then zoom in. So you can see the individual time domains for all your different channels. Again, pretty clean. So that was a sign sweep. That's all your data. Of course, your data can be exported, can be reported. Standard data export. Copy the graphics, copy your data, export it to universal file. It's all available right away. We go back to run window. Actually do it from here. I can then open up a random test. I'll show you how to set up a random test at the same time. Self-check, explain that in a second. Okay. So if you're not familiar with the MMP control system, you'll find that the layout is very similar no matter what test mode you're in. So you have your reference spectrum. Of course, now you're in acceleration squared per hertz. So when we set up our channels, the channels are set up exactly the same. However, the units are different. One thing I did not show, and I should have, I guess, in the other one, it's very unit sensitive. So if I set it to moment over here, set it to pounds force inch here, then it will only allow me to choose force gauges. Notice no accelerometers. Then I set my dimensions. One thing I should bring up, due to the large scale of some of these tests that are being run by NASA and some other major companies, there are times where we import the notch table to reduce chances of an operator error. And there's a format in the XML that we can use to automatically import directly from somebody else's export. Right. Running a random test. Now, our notches are coming on right away. I should have pointed that out. So if you look, you're at -3, and here we have follow schedule is right here, if you see it. this is due to the earlier parts of JPL. When we came up on level, the notches were hitting pretty hard. So with the additional weighting, you risked an overshoot. Now it starts notching at the very beginning and continues on. So if you look, you can see here's our overturning moment total. So on the force, I got the auto scale off. Very large numbers. There we go. So in this case, it's overturning on the around y-axis. This is probably due to the fact that I have the phase wrong. Again, for reporting purposes, I did not run throughput on this one, but we do have RMS data. See that how stable the system was over time. And then we can look at, again, individual force channels. These are very important. Then we can see where we notched. And this was 0. And that. The only other thing that I could show you was the, depending on how a customer wants to do it, for the preloading, we can do it in a scope mode, and which means you never have to break your setup, or you can use the online demonstration from Kistler, which I might not have open. I do not have open. No, there it is. Oh, here it is. Sorry, guys. Unfortunately, I don't have anything hooked up at this moment to the Kistler because I don't have a sensor. However, it'll give you the actual RMS or peak values. And of course, you can change the time constant from short to long. Thank you for your time. And let me know if you have any questions.
Yes, thanks a lot for this great overview. We definitely learned something. So, however, we had some questions. The first one I could answer by myself. So, yes, we will share the recording in the next few days with you, so you can go through the webinar again. Then there is one question for Bill. Are the sensors flight proven? The sensors are not intended to be used in the orbit, but what else has to be considered than outgassing, for example?
Okay. Force sensors generally have been flown. Okay, mainly the single component force sensors. Typically, you're not flying 3-component sensors. In this force limiting application. But yes, in terms of flying sensors, you usually qualify them to a specific test requirement from the specific customer. There's obviously low outgassing requirements in terms of cabling. And this could either be done by analysis based upon a clear materials overview, or the full assembly or cable assembly would be tested, to meet low outgassing requirements. So yes, there are certainly the piezoelectric instruments are flown, and they're qualified for particular applications as required.
Great, thanks a lot. Then another question also to you. Have you tested the long-term structural characteristics of these sensors like creep phenomenon, and possibly this sensor might be installed as a spacer and measure the comprehensive force for a bolt during the vibration test, and it will be left as a spacer?
Yeah, that's a good question. I don't recall seeing a report on a long-term test. However, I'll look into that. But fundamentally, the preload bolt has a fine thread to ensure self-locking of the preloaded sensor. So usually in this regard, there's really no further action required. But I mean, I understand your question, and and we'll definitely come back to you with a further comment if a long-term test was performed.
Thanks a lot. Now we are moving to Chris. So how about overshooting versus the limit value during applying notching? Do you know this one? Oh, Chris, you're muted.
Yep, sorry. Now I'm
Yeah,
unmuted.
sorry.
So when you set your notch values, you must always assume that they don't happen until it hits. So there's always going to be an overshoot. Depending on your sweep rate and your damping rate, your compression should be anywhere between less than 3%, or on a really high Q value, you can go up a little bit higher, but it is very mechanically dependent. It's very hard to stop a system from moving once it starts. We do have some other ways, and I can talk about that further.
Yeah, so maybe it makes sense to contact this guy directly. Mm-hmm. So another question, if my load cell is not in line with the test axis, does the control system allow me to multiply the sine or cosine of that angle n limit from that new channel?
Yes, we use the same thing, the vector add, but where you have the weighting factor, you would put in your cosine or sine values there. So you would have to have the two axis X and Y in there, each with the sine and cosine.
Great, perfect. Yes, then we are done. Many thanks to you, Chris and Bill, for this fantastic overview. If you have any other questions, do not hesitate to contact us via email or by phone. Thanks a lot for your attention, and have a nice day or night. See you soon. Bye, guys.
Bye-bye.
Thank you, Pascal. Thank you, everybody.